Okay, now that we understand basic contour integration, as well as the concept of a function being analytic with respect to the Cauchy-Riemann equations, we want to go to a new topic here. And this section is entitled Laurent Series, right, as well as something called the residue theorem. So these two concepts are related, and what we're going to do is we're going to develop this in a series of 3 lectures. So the first lecture is going to basically try to develop this Laurent series, Laurent, Laurent series. Now, I'm going to start by just saying something which is not what has been said before in this course. So the true definition of analyticity, we define the function to be analytic, complex analytic, if the Cauchy-Riemann equations are satisfied. But actually, the true definition of a function being analytic is that the function has to equal its Taylor series. So this is the true definition. And the reason why this definition is quite powerful is that it's valid not just for complex valued functions, but also for real valued functions. So a function must equal its Taylor series. But for complex functions, it turns out that this is equal to the Cauchy-Riemann conditions. Right, so this is actually a completely non-trivial activity to establish this, that the Cauchy-Riemann equations means that a function is equal to its Taylor series. So what we did was Cauchy-Riemann equations gave us the fact that the function was once differentiable, just once differentiable. And this is why in some textbooks you'll see that the satisfying the Cauchy-Riemann equations is sometimes termed holomorphic. So the function is holomorphic, but it turns out that the function being holomorphic is absolutely equivalent to saying that the complex valued function is analytic, which means that the function has to equal its Taylor series. So once again, that's beyond the scope of this course. Yeah, but for our purposes, we will often use the term analytic to mean the Cauchy-Riemann equations are satisfied. That's just the way that we're doing it. But I claim that that also means that the function is equal to its Taylor series. Well, what's the Taylor series? Well, here's the Taylor series, right? So Taylor series around a point z0 is just given by this expression over here, and this is the coefficient of z minus z0 to the power n, and this starts at n equals 0, which means just a constant term, and so on and so forth. But what's interesting here is that all of these entities are complex, right? So z is a complex number, z0 is the complex number around which we're doing the expansion, and this function is a complex valued function, and this is telling me that you're taking the nth derivative of the function and then evaluating at z0. But when you see this, you're probably going to question something, right? So for a function to be analytic, its Taylor series, the function has to equal its Taylor series, right? And of course, we don't really know whether the Taylor series converges because it's close to infinity. But in an open set around the point z0, you're anticipating convergence. Okay, now this is telling you, look, you need to be able to take the nth derivative, and n goes from 0 to infinity. You need to be able to take the first derivative, second derivative, third derivative, and so on. So that's a pretty powerful thing that you're saying here, right? To say that the function is equal to its Taylor series means that the function is at least C infinity. But for complex valued functions, we said that analyticity just means that the Cauchy-Riemann equations have to be satisfied, and that just tells you that the first derivative is continuous. So apparently, if this statement is true, that the Cauchy-Riemann equations being satisfied implies this statement over here that the function has to equal its Taylor series. Apparently, it's true that for complex valued functions, just having C1, which is what you're given in terms of the Cauchy-Riemann equations, that means that the first derivative is continuous, actually implies that all the other derivatives exist. That means that the function is in C infinity. And actually, it implies something a little bit even further than that, than the function is in C infinity. Now, this is pretty miraculous, right? This is not true for real valued functions. So for complex valued functions, this is saying you can differentiate it once, then you can keep on differentiating it. That's not true for real valued functions. So for example, if you take a real valued function whose graph is something like that, you can certainly take its derivative, right? So this would be something like the absolute value function. Its graph is like that. You can take the derivative, and the derivative is not going to be defined at that point. Right, so the derivative is not defined at that point, and then you want to continue. So it's possible to have a continuous function whose derivative is not defined. Okay, so if the first derivative of the function looks like that, then the second derivative is not going to exist because you're not going to be able to take the derivative at that point. So for real valued functions, C1 does not imply anything more than that, right? It doesn't imply that the second derivative is continuous, and this goes down to the fact that continuity does not imply differentiability, right? So because of this thing over here. But for complex valued functions, apparently you can differentiate it once, you can differentiate it infinitely many times. This is quite miraculous, and it's got to do with the fact that there's a very special geometry associated with the complex numbers. It's sort of like, because you're in something in R2, and you might remember that when you're talking about something in R2, if you're talking about limits, which are of course relevant when you're talking about derivatives, if you're talking about limits, for the limits to exist, you should get the same value coming in from every single direction, and that's a pretty powerful statement. And that powerful statement is something which leads to this fact. So for complex valued functions, C1 implies C infinity. Okay, but for our purposes now for this section, the idea of analyticity in a region around Z0 is that the function is equal to its Taylor series. So there you are. Okay, so as long as your Z is within the radius of convergence, you can just substitute values of Z into this, and you're going to get a value, right? So f of Z is going to be perfectly well defined. Okay, that's good. And another way of saying this is that there's no singularities, right? No points at which you cannot actually insert that Z value, because there's no problem here, right? So you can insert Z value here, all of these are powers of 1, powers of 2, and so on and so forth. All of these are perfectly well defined. Okay, so this analytic expression has no singularities, no values of Z where the function is not analytic, at least in a region around Z0. Okay, let's look at these functions here, right? So I'm going to look at two different functions. Here's one function and here's another function. And if I look at these functions, I realize that these functions cannot be analytic. They cannot be differentiable because they're not even continuous, right? So you can see that there's problem points at both of these functions because you're dividing by 0. So this is not analytic. This one is not analytic at Z is equal to I. This one is not analytic at Z equals -2 because you cannot insert that in, right? So then we are going to say that there's a singularity. So this function has a singularity at Z equals I. This function has a singularity at Z equals -2 because the denominator blows up. Right, so that's how we can think of singularities. Now it turns out that there's a difference between these two singularities, right? Notice that this one has a power of 2, this one essentially has a power of 1. So this is in some ways a worse singularity. It's blowing up quicker than the one which is blowing up over here. So we can define the order of the singularity as essentially that power. So this one has a power of 1, this one has a power of 2, so it's the order of the singularity is 2. So to extend this idea, we say that a function f of Z has a kth order singularity, where k is a counting number, 1, 2, 3, 4, and so on. K is a natural number. Has a kth order singularity if you can write f of Z in this particular form, right? So here's your kth order singularity at Z equals Z0. The numerator, you want this to be perfectly okay. So the numerator is some sort of complex function, and we are going to think of that as analytic. So a kth order singularity function f of Z has a kth order singularity if you can represent it in this form where the numerator is analytic, and there's your kth order singularity. Okay, so what's pretty nice about this is that, well, if I multiply this by Z minus Z0, I'm going to get G of Z. Well, G of Z has to be analytic. So another way of saying this is that this particular combination is analytic if you're saying that you have a kth order singularity at Z equals Z0, where k is just some counting number, right? It could be 3, for example. Okay, so if I have a value of Z0 and a complex function f of Z, well, I have several options, right? So one of the options is the sorts of options that we were talking about before when we applied Cauchy's integral theorem, for example. F of Z may be analytic near Z0, right? So it's a perfectly well-defined function like e to the Z or something like that, or Z squared or something, right? So that's one possibility. Another possibility is that the function can have singularities. So a kth order singularity would occur if there exists a value of k such that this is analytic, right? Then we say that Z0 is a kth order singularity. So that's another option that can occur. It can be even worse, right? If this is not analytic for any k in it, then we say Z0 is an essential singularity. That means you might try to multiply this by Z minus Z0 to the 1000, and you still don't get rid of the singularity. And if so, it's an essential singularity. Whereas in these cases, if you multiply, by multiplying the function by this, you're going to get, by multiplying f of Z by this, you're going to achieve an analytic function. But if it's not possible to do that for any any counting number, then we say that it's an essential singularity. So a prototypical example of an essential singularity is e to the 1 over z. So that's got an essential singularity at the point z equals 0. So what this is saying is that you can try to get rid of this by, say, multiplying by z to the k e to the 1 over z. If you do that, that function that I just wrote down there is not going to be analytic at z equals 0. So the way that you can establish that is by taking limits as z goes to z0, z goes to 0, I'm sorry, and establishing that the limit actually does not work, does not exist for any value of k that you can choose. Even if you choose k equals 1,000,000, it's still not going to work. We're not going to be too concerned about these essential singularities over here, but what we'll do is we'll talk about something slightly different. So we talk about something where there's a removable singularity first, right? So if I have a function of this form, z squared minus 1 over z minus 1, given in this form, clearly I cannot put in z equals 1 because the denominator blows up. On the other hand, if I take the limit as z goes to 1 of f of z, when I take the limit, that's z minus 1 times z plus 1, z minus 1's cancel. So that's effectively, I have to take the limit of z plus 1, so I'm going to get 2, right? So this is defined. Right? So even though the function is actually not defined at the point z equals 1, the limit as you approach that is perfectly well defined. And this is telling you that it doesn't matter which way you approach that point, you're always going to get the same value. In this case, the value is going to be 2. So if I define a new function where my f is defined by this as long as z is not equal to 1, and then equal to 2 if z equals 1, then I've defined a new function. So by doing that, I filled in the gap. Yeah. So if it's such a situation is called a removable singularity, right? So it looks as if there's a singularity, but if you approach it, if you take a limit to approaching that point, there's actually no problem, right? So that's another class of singularity. But we are most concerned about kth order singularities in this section. So let's look at this example. So let's suppose we take a function f of z equals sine z over z squared minus 1, z minus I. So sine, we already established, is a perfectly analytic function. So basically what I'm going to get is I'm going to get singularities of this function whenever the denominator is equal to 0. So that's z equals plus or minus 1, and that's z equals I. So there's 3 different singularities in this case. Okay. Now another bit of terminology, singularities are also sometimes called poles, P-O-L-E-S, right? So it's a pole. A singularity is called a pole. And now in this case, because here's my denominator, I can write it in this way. I notice that all the singularities are first order, right? So that's got z minus 1 to the first power, z plus 1 to the first power, and z minus I to the first power. So these 3 poles, you see, singularities are all first order. If it's a first order singularity, another term that is sometimes called it's called a simple pole. A simple pole is an equivalent terminology for saying that it's a first order singularity. Okay, so simple poles are kind of nice, as we figure out. Okay, but if you do have a pole, that means that your function is not analytic. You need to multiply it by z minus z0 to the k, yeah, in order to make it analytic. And that's what I'm saying over here. Okay, so if this is so, I mean, clearly I cannot write down a Taylor expansion for f of z because that by itself is not analytic because it's got a kth order pole at z0. So what I want to do is I want to extend this idea of a Taylor series. Can I get something like which is sort of like a Taylor series, which is related to this? And that's what we're going to do here. And that's going to be a Laurent series. Now, how do you do this? Well, the point is that if I define this function, then that's going to be analytic, right? That's the whole point. If I multiply by z minus z0 to the k, then the pole sort of disappears. So this function is analytic. And if that function is analytic, I can write down a Taylor series for that around the point z0. So I've got a constant, then I've got a constant times z minus z0 to the power 1, then a constant times z minus z0 to the power 2, and so on and so on and so on. But these constants, right? We'll bear in mind that these constants can be complex valued constants. Okay, fine. And what are the bn's? Well, here's our standard Taylor formula for the bn's, right? So you need the nth derivative of the function evaluated at the relevant point, and then you need to divide it by n factorial. Okay, so f is not analytic, but this g that I construct by multiplying through by z minus z0 to the k, in situation where f has a kth order pole at z0 is analytic, and I can write down a Taylor series for this. Okay, So that means that I can write down this statement here, right? So this is what I had before, but then again, g of z is equal to z minus z0 to the k times f of z. Okay, so what I want to do now is to try to figure out what f of z is. But first, what I'm going to do is I'm just going to do a little bit of something which seems a little bit strange. I'm going to rename a new bunch of constants with a with subscripts as opposed to the b. So I had b0, b1, and so on, right? And bn and so on. So I'm going to just rename them with in this way, right? So here's how I'm going to choose my a's. My a to the subscript minus k plus n is going to equal bn, right? And this is valid for all n in n and actually also in 0, right? Also the point 0, right? So n equals 0 actually works as well. So why does n equals 0 work? Well, here's n equals 0, right? b 0, right? So b this is n is equal to 0, so that's equal to that in that case. Okay, so what am I doing here? So b0, it seems like I'm going to rename that as a minus k plus 0, right? So b0 is the same as that, right? I'm just renaming. This is nothing more than that. b1 is, I put a 1 over here, so I have minus k plus 1. So this b1, I'm going to label it as a to the minus k plus 1, and so on, right? So b2 is minus k plus 2, and so on, and that's b2, and this goes on like this, and then what I'm going to get over here is when I'm looking at the k minus first power, I'm going to get a negative 1. And why is that? Well, b2 is the second power, so bn is going to be the power when I've got n up there. So that's what bn is going to be. So if I take n equals k minus 1 here, if I put n equals k minus 1 here, that's going to give me my coefficient of z minus z0 to k minus 1. But if I put k minus 1 here, what I'm going to get is minus 1. Right, and then I'm going to get a0 and a1 and so on and so on. So these powers keep increasing. Okay, so now what do I want to do? I want to find f of z. I want to get a series type expansion for f of z. So all I have to do is I have to divide by z minus z0 to the k. So I go ahead and I do this division. So I got that divided by z minus z0 to the k. This divided by z minus z0 to the k, but I got one factor over here, so I'm only going to get k minus 1. I got two factors here, then I'm going to get k minus 2, and so on and so forth. If I come to this point, I'm dividing it by z minus z0 to the k. So I'm going to get a minus 1 left over. So that's 1 over z minus z0. So a minus 1, z minus z0. And then this term is quite nice because when I divide that through, the z dependence disappears. I just get an a0. And now I got z minus z0 to the k plus 1. When I divide it by k, I just get one of them. Right, and so on. So my f of z is given by this expression over here. So here's my rewriting of that. So it's a whole bunch of terms like that, and then it's a bunch of terms like that. Now at this point, you will probably realize why I did this peculiar relabeling. My b's, I call them a's instead, because if you look at what's going on here, so there's a power of 1 over there, and that's an a1. So there's a power of 2 here, and that's a2. There's a power of 0 here because this is my z minus z0 to the 0, right? So there's a 0 here, and if I look at this is z minus z0 to the power negative 1, and therefore I've got the negative 1 over there, and so on, right? So this is z minus z0 to the negative k, so I'm calling that a subscript negative k. So the a's are set up so that the subscript of the a is exactly equal to the coefficient, to the power of the term z minus z0 in this expression. So here is a series of some sort for f of z, but f of z is not a nice function in the sense that it's not an analytic function, but it's a function which has a kth order pole. But even so, this function has a kth order pole. You're able to write it as some sort of expression, and the expression includes all the positive and 0 powers, right? Power 1, 2, 3, and so on, 2, 3, and so on, and this is the power 0. So it includes that part, but it also includes the negative powers, right? So that's z minus z0 to negative 1, and so on, all the way up to this point. It doesn't go off towards infinity in this direction. It stops at this point because you see this has a kth order pole. So if I multiply everything through by z minus z0 to the k, it's going to be a perfectly well-defined function, right? So it only goes towards the negative values up to this point over here. here. So let me point out that this part, the yellow part that I put out here, it would be sort of very much like the standard Taylor series terms. It has powers which are natural numbers, including 0, and that looks like a Taylor series. But there's more to this than that. There's these green terms as well, where you have negative powers. Right, negative powers. And how many of these terms are there? Well, this is to the power 1, so that's the power k. So there's actually k of these different terms. So you have k terms over here related to negative powers of z minus z0. And the reason why you have this is because you have a kth order pole. And this expansion is called a Laurent series at z0. So it's a generalization of the concept of a Taylor series. The Taylor series is analytic, and it's only going to have these yellow terms. But if you have a kth order pole, you can stick in these terms corresponding to negative powers as well, going all the way back to the relevant order of the singularity of the pole, and that gives you a Laurent series at z0. Okay, so how do you find the coefficients of the Laurent series, right? So at this point, the coefficients I've just have them just labeled with these things over here. So how do you find that? Well, this is what we had before. So g of z was perfectly okay, and g of z is given by f of z multiplied by that. G of z is perfectly fine, and we actually know what these coefficients are. They're in terms of the derivatives of g. Right, so we know what the b's are, but then our relationship between the b's and the a's, where we did this sort of peculiar shift, was that a to the minus k plus n is equal to b to the bn. Okay, so that means that a minus k plus n is equal to bn, and bn is given by this expression over here. And what's that expression? Well, it's 1 over n factorial times the nth derivative of g. So it's the nth derivative of g. What is g? G is equal to this this expression over here. So I take the nth derivative of g, which is all of that, and then I need to evaluate it at z0. So I evaluate this at z0. So this gives me an expression for my terms in the Taylor series, in the Laurent series, and actually, and the fact is here that n takes all values 0, 1, 2, 3, and so on and so forth. K is something which is given to us because we are given a kth order pole. For example, k might be 3, that's a third order pole, and then this would be a to the minus 3 plus n, and here's our formula, and you keep on putting in n equals 0, 1, 2, 3, 4, and so on to develop the values of the a's. So for example, if I put in n equals 0 into this expression, n equals 0 in this expression, I get a to the negative k, and that's my sort of worst term. That's my last term because I have a kth order. So that's it, right? So it doesn't go any beyond that. That's the term associated with actually the negative k power. So I can get that by putting in n equals 0. So if I put in n equals 0, I get a to the negative k. What happens when I put in n equals 0 onto this side? 0 derivative means that you don't differentiate the function at all. And this function here is g, right? So this function is g. So that's just going to give me my 1 over 0 factorial times g of z, and 0 factorial is 1. Okay. Next, if I put in n equals 1, I get 1 over 1 factorial times the first derivative of g. So it's that, and so on, right? So you can actually figure out these coefficients as you proceed. So let's look at a simple example. Let's take f of z equals e to the z over z squared, and I see that this has a second order pole at 0 because this z squared is something I can write as z minus 0 squared, right? So that gives me a second order pole which is centered at the point 0. Okay, so that's fine. And down here what I've done is I've written down my expression for in general for trying to figure out what the coefficients of the Laurent series are. So what I want to do is I want to try to figure out what the Laurent series of this function looks like. Okay, so first thing I noticed that we said it's a second order pole, so I'm going to put in k equals 2 into this expression, right? So over here I'm going to get minus 2 plus n, so k is equal to 2 up there, and that's something that's pretty nice. And if I put k equals 2 up there, and of course z0 is equal to 0 as well, right? So if I define my g of z to be, well, I just multiply the z squared onto that side, so that's e to the z. So here is g of z, which is analytic now. by multiplying by z minus z0 to the power 2, I have made the function analytic because f of z has a second order pole at z equals z0. So g of z is that function here, and this is g of z over here as well, right? And what this is telling me now is that this is equal to down here. So I have 1 over n factorial, and then I have the nth derivative of g of z evaluated at z0. So it's given by that because z0 is equal to 0. So my a with subscript minus 2 plus n is given by this expression. Okay, now can I figure out what gn of 0 is? Well, this is a nice function because if I take one derivative, I get e to the z and so on, right? So e to the z is what I get for any derivative. Each and every derivative is e to the z. If I plug in z equals 0, e to the 0 is 1. So the nth derivative is equal to 0 for all n, right? For all n in n, and also at the point 0 as well, right? So so maybe I should say, I could say union. Okay. So what this tells me then is if I look at this expression that I have over here, a to the negative 2 plus n equals 1 over n factorial, but I just figured out that the nth derivative is equal to 1. So it's just equal to 1 over n factorial for every single value. Okay, that's really good. And basically what you do here is you have to keep on plugging in n equals 0, 1, 2, 3, and so on in order to get the coefficients. Okay, so let's see how that goes, right? So here is my my general Laurent series expression for kth order and general z0. So I have these bunch of sort of the bad terms which have negative powers, and then I have the positive powers over here. But let's remind myself that k is equal to 2. So this term is a negative 2 is what I get here. So a negative 2, and that should be a power of 2 as well. And z0 is equal to 0. So the denominator here is just simply z squared. Right? So that's z squared, and then I have a to the negative 2 at the top. So how do I get a to the negative 2? I need to put in n equals 0 over here. 0 factorial is equal to 1. So 1 over 0 factorial is equal to 1, and that's the expression that I have over there. Okay, that's that term. What about the next term? Well, the next term is this term over here. And in order to do that, what I do is I put in n equals 1 because I put n equals 0 already. So when I put in n equals 1, I get a to the minus k plus 1, and that's associated with this power over here. But k is equal to 2, right? So if k is equal to 2, this is 2 minus 1, so that's the first power. Z0 is 0, so I get z in the denominator, and in the numerator I have a to the minus 2 plus 1. So from here I put in n equals 1 in this case. Right, because it's minus 2 plus 1, I put n equals 1, so 1 over 1 factorial, which is just 1. So that's that. And then I realized that, look, in this expression, I have to go all the way down in powers until I get z minus z0 to the power 1. So I'm already here. Right? In this case, I'm already here. So this part, which in general has k terms, in this case only has 2 terms because k is equal to 2. So I'm done with that, right? So I come to that point. And what happens next? So next I need to figure out what a0 is. So a0, so this is again minus 2, right? So over here, right? So minus 2 plus n. So now what I do is I put in n equals 2. Right, in order to get a0, I put n equals 2, so I get 1 over 2 factorial. That's my a0, and similarly the next two terms, right? So this term is a1 times z minus z0 to the power 1. Z0 is 0, so that's just a z to the power 1, and then a1 is equal to, well, I put in n equals 3 here in order to get a subscript of 1, so it's 1 over 3 factorial, and then this is 1 over 4 factorial, and so on. So what I've circled here in pink is a Laurent series of this function around the point 0. So it's a function which is not an analytic function. So it's going to have negative powers in its series expansion in powers of z, and the worst negative power is -2, and then there's a -1, and then it's 0, 1, 2, 3, and so on. So from this point onwards, things are good, but these are the terms which correspond to the fact that it has a pole of order 2. So I'm going to get 2 different terms over here. Okay, so we'll stop here, and in the next example, in the next lecture, we're going to extend this idea of Laurent series to come up with some powerful integral theorems.